Okay, thanks for everyone's attention. This is collaborative work with Professor Shigang Chen and Ming Chen in University of Florida. So the title of our presentation is Joint Property Estimation for Multiple RFID Tag Set using the snapshot of variable length. So here this slide is about the brief introduction of RFID system. Because the previous presenter already gave that introduction. So here I just want to emphasize one point. The popularity of our RFID system is because they do not need external batteries. They can harness energy from the continuous radio wave emitted from the nearby RFID readers. That's the key advantage of RFID system. So now the new trend of RFID system is as follows. Intel has promoted their new generation of RFID tag called whisper tags. They can not only report tag ID, but also provide additional sensing capacities. For example, it can report temperatures, moistures, and accelerations. And many engineering work are devoted to reduce the energy profile for computation component memory using RAM and the sensing component. So this is what's happening in the industry world. Here is one typical applications for the for these sensing tags. For example, in the cold chain monitoring, in the past, one or several temperature and moisture sensors are deploying within a car to let people know what is happening in the car during the transportation. So this is the past situation. Now with this kind of new sensing tags, people can deploy these tags for each box. So in the past, in future, the end users can sit before their PC, their desktop, and check the current status of their ordered goods. So this is what industry guys they are doing to push the IoT system into real application. Nowadays, our lab is even collaborating with a company in Wuxi, one city in China. They have found a way to recycle this tag, to recycle this box after the product delivery. So as the previous panel discussion said, the key point to push IoT into practice is to reduce the cost of deploying these kind of devices. So we do not have batteries, and their deployment costs and their usage costs can be reduced. That's why RFID system become quite popular these days. So this is what's happening in the industry world. So what can we academies do for research? So for RFID research, the previous scholars they studied how to collect information efficiently from a single set of tags. They studied how to collect tag IDs. They also studied how to estimate the cardinality of the tag set, like they can estimate the number of tag within a set. That's the previous research. However, I want to emphasize here that we always need to co-analyze multiple tag set, not just a single one. Why? Because for a warehouse, as an example, we typically need to deploy multiple readers to implement the full coverage of a large region. Here is one example. We need to co-analyze the tag set at reader 1 and reader 2 and reader 3. That we need to know their we want to know the number of tags in the unit of the 3 set. And here is another example. As time passes, and we can know the tag set covered by a single reader, they may change over time. And some tags, maybe the blue tags may be moved in the past, and the red tags, they are moved in during these intervals. Sometimes we want to know how many tags have been moved in, some tag has been moved out. This is another example of co-analysis of multiple tag set. Here's another example. This is a typical example we want to emphasize in our paper. Like in a supply chain, the tagged product, they will be transported from one location to the other. For example, we can transport the product from the factory to wholesalers and to end retailers. We want to know like how many products have been transported from like the factory 1 through the wholesaler 2 and finally to retailer 4. And for this traffic flow, we want to emphasize what's the scale of this logistic flow. This is a very useful applications for RFID system, for large-scale deployment of RFID tags. We abstract all these previous applications and examples into one problem called multiple tag set joint property estimation problem. We just assume we have very simple assumptions, and we just assume there are multiple like k number of tag set. These tag sets are of interest to end users, and they are scanned and or captured by the RFID readers. We use the symbol S1, S2, and SK to represent this multiple tag set. Here in this figure, we just illustrate 3 tag sets, S1, S2, and S3. And for these 3 tag sets, they can form an arbitrary set expression as connected by the typical set operators like union, intersection, complement, or relative complement. And here we now we have an arbitrary set expression and arbitrary number of tag sets we want to co-analyze. And this problem is to estimate the number of tags or the cardinality of such a set expression. This is called the joint property of K tag set. Now the key difficulty is that if we have K tag set, then the number of possible set expression could be really huge. And we want to tame the complexity. So we just start from the elementary subset. So you can see in this figure, if we have 3 sets, S1, S2, and S3, we can divide their union into 7 elementary subsets. And we just limit our focus to how to estimate the number of tags in each of these subregions. If we can know the size of this elementary subset, then the cardinality of any set expression can be derived. Here is an example. This can be derived just using quite simple set transformation technique. Okay, now we can formalize our problem, and we know everyone in such a short time they hate the formalization, they hate symbols, but we have to use something. So we use the symbol NX to represent an elementary subset, and using the symbol small nx to denote the cardinality of such an elementary subset. And we want to guarantee that this elementary subset size can be estimated with bounded error. That's the problem formulation. And we also want to consider to estimate the cardinality of the union of all sets. This is called a composite joint property. This is the problem formulation. So this is a research problem not confined within the RFID research domain, but also useful in many other research domains. For the related studies about the multiple tag set, there are many related studies like missing tag detection, identification, continuous monitoring, unknown tag identification and estimation, and also missing tag detection and the differential estimation. You can see that this problem, they all cope with just 2 tag set, like M prime and N, and they want to estimate quite simple set expression, just 2 tag set. And our problem is we want to give estimation for the cardinality of any set expression. This example is just for three text set. And the previous work, they have actually two common problems. First, they specify the accuracy using the relative error bounding model. And as we know, for accuracy, for estimation accuracy specification, there are basically two ways. One is to bound the relative error, and you can see this equation. And the other way is to bound the absolute error within a bound like theta. And for this example, it's bound the relative estimation error within epsilon, and at a probability of at least 1 minus delta. These are two basic ways to specify estimation error, and we found that it's incorrect to use the relative error model, because for elementary subset nx, it can become exactly empty. Its size can become 0. In that extreme case, if we want to satisfy this above accuracy requirement, then its estimated value nx with hat must be exactly 0. Otherwise, we cannot satisfy this this equation. So this result is impossible to realize. So we argue that we just forsake this kind of accuracy specification. We need to bound the absolute error instead. So this is one problem about the previous work. And the other problem about the previous work, that they used identical frame size to encode each text set. Their intuition is like that. So we have three text set, the first one, the second one, and the third one. We just encode each text set using like the Aloha frame or bitmap of the same size, so that the three text set that can be combined together using Bitwise OR. So we can so in this way we can get the snapshot of the union of the three text set. If we know the union, then we can further derive the size of the intersection using the famous inclusion and exclusion law. So you can see this set expression about intersection that can be transformed to the summation result of several union set cardinality. So this is what previous work does, and why they assume each text set must be compressed into equal length bitmaps. And we argue that it's impossible, it's difficult, or even impossible to use identical frame size. And first, there's no mechanism in reality to impose an identical frame size for all RFID readers for distributed system. This is one major obstacle. And the other is, if we use the same frame size to encode each text set, this will become quite inefficient. Say, if we have a small text set, then we have to use a short frame, of course. But if we use the short frame to encode the large text set, like 200 tags, then this short frame will become overly dense, and all of its time slot will have tag response. So it will become overclouded. So for such a large text set, we need to enlarge the Aloha frame or the bitmap size. So if we apply this large Aloha frame or bitmap to just a small set, so you can see most of the time slot will become empty. So that's a dilemma. So we just so our intuition is to use the small Aloha frame to encode small text set, and use large frame size to encode the large text set. This adaptive Aloha frame scheme is quite common in the RFID world. Like for the EPC global standard, they use the Q-digest algorithm to adapt the frame size. So we follow the similar idea. We want to adapt the size of the bitmap or the size of the Aloha frame. And in this process, we must satisfy the accuracy requirement of joint property estimation. So now, if we are given k aloha frame or bitmaps with different lengths, we denote them by B1, B2, and BK. With no loss of generality, we just assume the length of B1 is M1 is smaller or equal to M2 and follow this equation. So for this k bitmaps, we can apply the operation of extended bitwise OR to combine them. So you can see we can replicate B1 for several times so that it will have the same length with the longest bitmap B3 here. And the B2 is also replicated for twice. So after the replication, after the extension, all the 3 bitmaps, they can be combined using bitwise OR. So we can get this OR bitmap. So for how we can extract the joint property information from the extended bitwise OR operations, that's the key problem. And note that we can apply the bitwise OR operation to any subset of the bitmap of B1, B2, and BK. So the resultant bitmap can be denoted by OR with the suffix Y, and the Y denote whether each bitmap they participate in the bitwise OR operation. So for each OR bitmap, and here we have 2 raised power to k OR bitmaps, and we use the symbol ZY to represent its proportion of 0 bit, and P is the common sampling probability. In most cases, we configure P to 1. So this is the input parameter of our joint property estimator. We just know the proportion of 0 bit in each of the 0 bit map, this OR bit map. Here we have OR111. It represents B1, B2, B3, they all participate in the OR operation. You can see the 3 bit, they can change from the 1 state to 0 state. We have many of these OR bit maps. And we have given the closed form estimator for the union of text set cardinality. N0, the complement of N0. You can see the N0C is equals to this equation, and UY here is the measurement about the number of tags in the OR bitmap ORY. That's the closed form equation for the number of tags in the union set. And here we have, if we want to estimate the size of each elementary subset, like here, we have N001, N011, and Zn111. For this, for all these kind of cardinalities for elementary subset, we have an equation to estimate their cardinalities. So you can see the U definition is the same with the previous slide, and M is an equation, is a matrix following this equation. And we have, and in our paper, for the details, you can see in our paper, we have proved that this coefficient matrix M is non-singular. And we have also provided a closed form equation to directly calculate this inverse matrix, the inverse of M. So you can see all the joint properties they can be estimated using this matrix transformation. So here is a short summary. Here we have provided a generic algorithm to estimate the cardinality of an arbitrary set expression comprising of k set. And note that this k set are not necessarily RFID text set. All theoretical results can be applied anywhere in like traffic measurement and in some other mining technique, data mining domains. And we just assume this text set, they have been compressed into bitmaps with possibly different lengths. And in RFID domain, it's quite easy to implement this assumption. And we will show that it's also efficiently to do so. use some kind of frame adaptation scheme. In our paper, a significant proportion of our paper has been divided to analyzing the statistical property of our estimators. And we have proved that our estimator is unbiased. And we also need to satisfy the previous accuracy constraint. And we convert that constraint about absolute estimation error into these two equations. We just bound the estimator variance. And later we will show how to analyze the variance. After a very long, tedious analysis, we show that if we compress each text set using a frame size of this length, then we can guarantee the estimation accuracy can be satisfied. And we show that the load factor of each aloha frame should be at most this bound, and it has been influenced by the S max and the K max. The S max is the tied upper bound for the size of any text set, and the K max is the largest number of text sets involved in a user query. Here is the simulation studies, which I just want to skip the tedious proof about the estimated the variance. Here we just show the simulation result. We just assume there's a multi-location distributed RFID system with following parameters. So you can see the text product that they can be transformed. They can be transported from location A to location B and then to location C. We assume at each location, the average size of a text set is 10,000, and the maximum size of text set is about 50,000. So you can see the normal flow of text object is much smaller than the worst case number the system is designed to handle. So 50,000 here is the S max. You may wonder whether it is realistic to assume such a large size of text set, like it's about 10,000. In fact, it could be it is possible. And in our lab, we have set up this experiment test bed. We have three image readers with number R402, and each reader can be attached with 32 such antennas. They can cover a huge area in a warehouse. So we assume each text set its size is taken randomly from a normal distribution, with the center with average value to be 10,000, and its variance is 2,000, and it's truncated by the range between 0 and S max. And this is for accuracy requirement configuration. Well, we want to compare our algorithm with the algorithm called INC EXC, which is based on inclusion and exclusion rule. And this protocol, they encode all the text set into bitmaps with the equal length. And the other work is called CCF, Composite Counting Framework. And this algorithm, they encode the text set by K-mean algorithm. K-mean algorithm is quite a well-known and a common technique used in traffic measurement. And we show that this algorithm is not suitable for the RFID domain. It's also not compliant with the EPC global standard. So we show that if we compare the protocol execution time, the time efficiency of all the three protocols, our algorithm is at this level. And the inclusion-exclusion rule, that kind of algorithm is at this level. And the K-minimum encoding scheme called CCF is at this level. So you can see for our algorithm, we adaptively encode each text set with different length aloha frame. You can see this ladder climbing up. we adaptively to encode each text set. This is the main motivation, the contribution of this paper. And we also show that our algorithm is influenced by the number of text sets involved in the text set co-analysis. If like 8 number of text sets involved in the co-analysis, we show that the frame load factor must be decreased in order to meet the accuracy requirement. And we also show that in order to meet the accuracy requirement, the time cost of our algorithm is also much smaller than the previous work. It's like 10 times smaller, 5 or 4 times smaller than the previous work, inclusion exclusion rule or the CCF protocol. So our algorithm is both more accurate and also much cheaper. This is another accuracy comparison on the different parameter settings. So we can skip this part. This is the final conclusion of our paper. So we show that we have convinced you that joint analysis of multiple text sets is important and really useful. And we have identified 3 inadequacies about the previous work for the RFID joint property estimation. They typically estimate the joint properties of only 2 text sets. We can deal with multiple text sets, and we can estimate the cardinality of an arbitrary set expression. And the previous work, they incorrectly bound the relative error. And we show that it's better to bound the absolute estimation error instead. And the previous work, they ineffectively and inefficiently adopted an identical fixed frame size scheme. They encode each text set with equal length aloha frame or with equal length k-mean snapshot. This is incorrect, and we use adaptive protocols, and we can support different and adjustable frame sets instead. So this is the key contribution of this paper. And the following part is about the extra slides about the various analysis of our estimators. This is really difficult and tedious part. You can just skip it. You can just see the final result. After all this analysis, we just show that it's better to configure the frame size, the load factors to satisfy this inequality. So this is the end of my talk. Thanks.